Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today we're continuing our look at flat earth engineer Brian Mullen. Today we're going to discuss his theories on centripetal force in orbits. So let's cue up the music and get going.
The gravitational force that's supposed to hold our Earth to the sun, make it orbit the sun, is really a centripetal force, and this is the theory. Okay, so what a centripetal force really is a force directed towards the center of a circle. So a ball on a string is the best way to give an example of this. You have a ball or a mass, a little foam spherical Earth here, and a string representing the force pulling it towards the center, which in this case would be my hand, where you could say that was the sun. So you spin this around. Okay, the tension in the string is the force. Okay, and that creates a velocity. The ball resists that force by traveling in a circle around the center point, or the sun in the case of the solar system model. Okay. So I have written down the equation for centripetal force over here. It says centripetal force is equal to the mass, or the ball, times the velocity squared divided by the radius. So the velocity would be the speed that it's traveling at around the circle. The radius would be the length of the string in this case. Or if you look at the solar system model, which I've got drawn right here, with just the Earth and the Sun, it would be the velocity, the instantaneous velocity of the Earth at any point around the circle, and the radius would be the distance from the Sun, and the mass, of course, would be the mass of Earth. Alright, so it is the mass of Earth, not the mass of the Sun. Remember that.
Okay, now I really don't have any problem with what Brian is talking about. I'm following along just fine. It's not an issue to me. His formulas, of course, are correct. Now, what he's talking about is centripetal force acting between two bodies that are in orbit. We have the Earth up here as M1, and then it's orbiting around the Sun, which is M2. And the way he's describing it, the centripetal force is acting between those like the string on the ball. That's not really a good way of looking at it. I think a better way of looking at it, since he wants to include gravity in all this, is let's make this gravity. That's the force of gravity. And it's opposed by what we call centrifugal force. Now, the formula for centrifugal force is exactly the same as the centripetal force. It's just in the opposite direction. So we have gravity trying to pull the Earth into the Sun, and that's equaled by the centrifugal force trying to pull it out of orbit. Now, as a result, since those forces are balanced, the Earth just basically goes around in orbit, essentially weightless. Now, the other thing that we can imply from this is, since the force of gravity has to equal the centrifugal force for an object to be in orbit, we can set that equation equal to that one. So let's go ahead and see what happens when we do that. Now, here's another thing that Brian gets correct. Okay, when we set these two equations equal to each other, we can actually factor them a little bit. Now, obviously, this is the force of gravity. That's centrifugal force. They're both forces. Manipulating this or simplifying these equations don't change the fact that the bottom line is we're comparing the force of gravity to centrifugal force and setting them equal. So there's an M1 right here, and there's an M1 right here. They can be factored out, like so. Now, another thing that we can do is we can actually get rid of one of these r's. So we can make that r, and we can make that v squared over 1. But we're going to hold off on doing that right now, because I want to go ahead and let Brian explain this for a couple more minutes.
The mass of Earth, just like the mass of the man in episode 2, cancels out. Kind of funny how this gravity equation kills the smaller mass. Anyway, it's nature, right? That's what we're told. So now you have the mass of the sun, you've got the velocity of the Earth, which you know because you know the radius of Earth, and you can calculate the circumference of the circle, or the distance it travels around the sun, which circumference, I'll write that over here, is equal to 2 pi r. Okay? So they already knew the distance, so they can figure out the velocity, because velocity is really distance over time. So what they can do is say that velocity is equal to 2 pi r, and we'll call over that over big T. In physics, big T is usually considered a period, or the time it takes to make one revolution, which in this case they thought was 1 year, because the sun does its thing in 1 year. 4 seasons it takes, though they tell us 365 and a quarter days, which actually comes out to 31,557,600 seconds, which is what you would have to do to make all these units work. But I'm not going to go through all the numbers. I'm just going to show the algebra to show how this was done. You can look this up. This is all over the internet. So we need to isolate the mass of the sun. We have everything else. We have the velocity, which can be calculated with this equation. We have the radius. Radius is the same over here, and they have the gravitational constant, which who knows how that was really determined, but it doesn't matter. Okay, so showing some simple algebra here, you could say multiply this side times r squared over g, multiply this side times the same thing, r squared over g, just to show the steps. So r squared cancels, g cancels. Over here you've got r squared times v squared over g times r, and then this r cancels. So you really just have r times v squared over g is equal to the mass of the sun. And that comes out to 1,988,500 times 10 to the 24th kilograms. And this is many, many times more massive than the Earth. The Earth is actually 5.97 times 10 to the 24th kilograms, I think. Is that written down? Yep, roughly.
All right, so I'm really pretty much in agreement with what Brian's done. That is one way of finding the mass of the sun. I don't have a problem with that. However, that's not the question that we're dealing with right now. We're dealing with orbits, centrifugal, centripetal, and gravitational force, and the interplay between those and how orbits work. The mass of the sun is irrelevant. But what the take-home message that you can use is that mass 1, the mass of the satellite, factors out of the equation. So the mass of the satellite doesn't matter if it's a tin can or a planet. It'll still orbit at the same distance and the same speed. Now let's go back to Brian for a moment, and I want to discuss something that he's doing. Now once again, he's putting a tremendous amount of math out on the whiteboard. What he's done here is he's basically done his 2 pi r over t and squared it, came up with this term right here, and he's using that as a substitute for v right here, or for v squared I should say. So there's a lot of math involved here. And then he's come up with this equation right here. And I want to go ahead and address that specifically. Now what he's done here is he's tried to relate the radius of an orbit, which is this between the Earth and the Sun, for example, to the period of the orbit squared with these constants and taking the cube root of it. Now, this is a rather complex way of doing something. And one of the problems that you run into with math is it's not simple arithmetic. You have to have some insight and some ability to see what's going on and then figure out how that will be useful to you. Let me show you what I mean here. And I think that once you follow along, it'll make it very easy for you to understand. Now, the first thing that I want to do is let's get rid of this cube root. Now, if we get rid of the cube root, we have to cube r, because that was the whole purpose of the cube root. Now, let's look at these numbers over here. Now, is G a known number? Yes. Is the mass of the sun a known number? Yes. Is 4 a known number? Yeah. Is pi a known number? Yeah. So we're going to rewrite that a little bit. We're going to say that r cubed equals a constant times t squared. Starting to look a little familiar? Because we took all those known terms and just put it into k, because they're not going to change from equation to equation. Now, do you remember what we had earlier, and that was a proportionality? Something like this. Which would, of course, be Kepler's third law of planetary motion. Okay? But there's something else that we can do. Let's get rid of this t here and put it down there. That equals k, which is a constant. Now, what's kind of interesting about that? If we know the radius of an orbit around a body and the orbital period, that's a useful proportion that we can use. Let me show you why. All right, so let's look at the ISS. Now, the ISS orbits 400 kilometers above the surface of the Earth. So the radius of the ISS's orbit is the radius of the Earth plus 400. And this, of course, is in kilometers. The orbital period of the ISS is 92 minutes, but we'll use 90 just to kind of even it out a little bit. Now, here's an interesting trick that we can use. All right, so let's remember our relationship. I always reverse those for some reason. We know that R3 over t squared equals a constant. But let's do this. Let's call R3 6371 plus 400. And we'll cube that. And we'll put it over 90 minutes. And we'll square that. Now let's set that equal to something. We know that the moon orbits the Earth once every 27.3 days. How many minutes is that? We can figure that out. But if we know that, do you think maybe we can calculate what the radius of the orbit of the moon is? Because if we have R3 over t squared equals a constant, we can take R1 cubed over T1 cubed or squared equals R2 cubed over T2 squared. It's kind of like the ideal gas law. Now, what happens here is that if we know the orbit of one body and we know the period or the radius of the orbit of another body around the same body, we can calculate the missing term. That's the beauty of Kepler's laws. Well, let's go ahead and put some numbers together. Now, the orbital, here's the basic formula. What I've done is I've rearranged it a little bit. So I've got the orbital period of the moon squared times the radius of the ISS cubed over the radius of the ISS squared equals the radius of the moon cubed. That was just basically rearranging the formula where we set the two proportions equal to each other. Now, the orbital period of the moon is just shy of 40,000 minutes, so I've squared that. The orbital period of the ISS is 92 minutes, but I went ahead and made it 90 just to make it round. And these are both in minutes, so they cancel units. The only thing left is the orbital radius of the ISS, which is 6771 kilometers, and that's cubed. Well, go ahead and do that math, and you'll come up with 389,799.5. Now, the actual radius of the lunar orbit is 384,400 kilometers. Why is the difference? Well, put 92 in there and see what happens. That number will get a little bit smaller. You know, I started playing with these numbers a while ago because I really like this little formula. We'll put it back to the original here. Because with that, if you know the orbit of one body, you can figure out a missing term in the orbit of another. So here's one for you to do at home. Now, as I said, that's the orbital radius of the ISS, and that's the orbital period of the ISS. Use that as R1 and T1. Then I want you to use the radius of the Earth, 6,371 kilometers, and I want you to tell me how fast the Earth has to rotate in order for an object on the equator to be weightless, basically in orbit. Now, go ahead and put your answers in the comments section of this video, because I've done that. It's kind of an interesting thing. Intuitively, you're going to be kind of surprised with what it is. And then why don't you go ahead and figure out what orbit an object would have to be in to orbit the Earth once every 24 hours. A geosynchronous satellite, for example. How far out would that have to be? You can answer that question with this formula, simply knowing the radius and the orbital period of the ISS. You'll be amazed at how easy it is to calculate. But let's go back on to Brian here.
How do you figure out the mass of the object that's orbiting the sun then? Because this says that the sun wins. The mass doesn't matter. I don't know. Well, what they say is they observe the object. They observe Jupiter, for example, and they observe the moons that they tell us are orbiting Jupiter. And they can tell by the tug and the pull back and forth, say like, I don't know, let's say that this is Jupiter and this is a moon, and they can see the little wobble it gets from the moon going around it, the wobble effect on the planet, that they can estimate the mass. Okay, and maybe they compare it to what they think is the relationship between the sun and the Earth. But it's all from observation. It's kind of guessing, I think.
Well, you know, I really love it when a guy that is a professional engineer expresses bewilderment about basic high school physics. You know, that doesn't really fill me with a lot of confidence for his ability as a civil engineer. I want to address this concept that observational science is nothing but guessing. Well, we do have something in science called a scientific wild-ass guess. And what that means is we think we know what's going on based on observation and data and statistics. We have reasons to believe this, but it is just a little bit of a leap of faith. It needs to be tested to see whether or not it's correct. So there was an astronomer by the name of Tycho Brahe. I'm sorry if I butchered his last name. But what he did was he spent an entire lifetime observing the orbital periods of the planets. And he did it with the moon and anything that he could get a hold of that had an orbital period. He observed it and recorded it. And he literally spent his entire life doing that. Now, after he was dead, the person that got a hold of his records was a guy named Kepler. He analyzed those records and came up with his Kepler's laws of orbital mechanics. And one of the cornerstones of those laws is this relationship right here. And that is the cube of the radius of an orbit is proportional to the period of the orbit squared. Now, that was based strictly on observation, and it allowed him to make some predictions, just as we made a prediction right here, and we were pretty doggone close. The problem that you run into with this proportion and the difference between a proportion and an equal sign is that there's got to be a constant of proportionality. One or both of those numbers has got to have a constant on it. that never changes. The only thing, if you change the radius, you change the time, you don't do anything with a constant. That just kind of makes it equal something. But we can actually take that proportion and use it without the constant, without knowing what it is. But the interesting thing is that Brian, in this video, actually derived that constant. That was that big, long cube root equation that he had. So he knows that there is a constant available, and he also demonstrated very clearly that when you took the constant out, that proportion worked. And I showed that over here a minute ago. So even though Kepler came up with this based on observational data, when Newton came along with the universal law of gravitation, that allowed us to actually calculate that constant and put a number to it. And as Brian pointed out in his video, if you know those numbers, you can actually calculate the radius or the period of a planet if you know the other value. So whichever one of these you know, you can calculate the other. And you can do that directly with no comparisons. Or you can compare two bodies. For example, we know the orbital period of the Earth. And by knowing the orbital period of the Earth, by comparing the orbital period of the Earth to the orbital period of those planets, we could determine relative distances. And the unit of measurement that we used was called an astronomical unit, which is the distance from the Earth to the Sun. We didn't know what that was, but we knew that Venus was 0.72 of that number. We knew that Mars was 1.6 or whatever it is of that number, or Jupiter was 10.6 times that number. But we didn't know what the distances were. Now, the way that we found the distances is we had to accurately measure the distance from the Earth to the Sun. Once we had that number, we knew the size of the solar system. And that was what the Great Expedition in 1769 to observe the transit of Venus was designed to do. It wanted to answer the question, how big is the solar system? And to do that, it needed to find out the distance from the Earth to the Sun. So this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for joining me on this. I hope you enjoyed it. We're going to continue through the rest of Brian's videos, and then we're going to go on to something else. So take care, folks.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore.